So last lecture, we were looking at, we just started looking at capacitances inside a MOSFET. And we said that if you look at the structure of the MOSFET here, what you find is that there are capacitances between each pair of terminals. We have gate here, we have source, we have drain, and we have body. And you can see here between each pair of terminals, there's a capacitance here. Between gate and source, there is CGS. Between gate and drain, there is CGD here. Between source and body, we call it obviously CSB here. And between drain and body, CDB here. And there's a capacitance between gate and body as well. And what we are going to do is look at these capacitances in the saturation region. Okay. And so I was telling yesterday that the capacitance that comes about between gate and source has two components. One component comes about because of the charge in the channel here. There's a charge in the channel, and as you change the gate voltage, the charge in the channel enters through the source or exits through the source, and it can do that through the drain as well. Okay, so anytime you change charge with respect to voltage, and we find here that a change in gate voltage here, causes charge to exit from the source or enter from the source here. So that's the source of the first term here, the capacitance that you see here. And because the channel charge is the source of this capacitance here. So what we have is, the capacitance is a parallel plate capacitance, C oxide is there. Along with that, the width of the MOSFET and the L here. The L that you see here, that's the other part here. So this is capacitance per unit area multiplied by the area of the channel, if you would like, the length multiplied by the width. And 2/3 comes about because, the channel is not uniform. When you apply a gate voltage, we know there's more of channel here and less of channel here. So it's a non-uniform channel, and that results in a prefactor here, 2/3 here. So that's one source of capacitance. The other source is that you have overlap between the gate and the source here, between the N plus region that you see here and the oxide or the metal that you see here. There's an overlap, and because of this overlap, there is another component to capacitance besides the channel. Remember, the channel starts from the edge of N plus to the edge of this N plus here. And so what we are talking about is not the channel in this case. We are talking about that there's a region of N plus which overlaps with the gate here. And that results in a capacitance that you see here. Okay, so that's the two sources of capacitance. This capacitance is specified as per unit length, and you have to multiply it by the width of the MOSFET to get this value here. And this capacitance, as I said, is proportional to area. Now remember, what we are doing is talking about capacitances in saturation region. The gate to drain capacitance is similar, except that the channel part doesn't contribute much to the capacitance here. So the channel component you can see here is missing in saturation region. And the reason is that once you go into saturation region, a change in drain voltage doesn't affect the channel. Okay, the channel becomes sort of independent of the drain voltage here, and that's the reason why you don't get a channel part here. Okay, so that component is missing. But if you were in linear region or triode region, then we know that the channel responds to the drain voltage here. The charge in the channel changes as you change the drain voltage here. Then you will get a component due to the channel as well. Okay, so this is in saturation region. So the only component that you get is the overlap capacitance. We call it CGD0, and this is CGS0. So these terms will be given to you. If depending on the technology that you use, CGSO will be known to you, CGD0 will be known, C oxide prime. All these are parameters which are known, and all you have to do is multiply by W, multiply by WL, and you get these two capacitances. This was the picture that I had shown of a MOSFET, the top view, and the top view here. And this picture we require for source to body capacitance and for drain to body capacitance as well. So note that source to body capacitance and drain to body capacitance both are PN junction capacitances. Okay, I have N plus here, and I have a body which is P type. and I have a PN junction capacitance, and these PN junctions, both of them are reverse biased. So it's a depletion capacitance that I have. Now, in this context, note that if I look at this source here, N plus region here, below that N plus region is all this P type here. Okay. So the capacitance that comes about will be the depletion capacitance per unit area multiplied by the area of this particular N plus region. Okay, because the below this is where the capacitance is, below the N plus here. Okay, so the capacitance will depend on capacitance per unit area multiplied by the area here, and the area is equal to the length of the source multiplied by the width of the source. Okay, similarly, here the area is LD multiplied by the width of the transistor here. So that's the width of the transistor. Now, in this context, what I was trying to tell you yesterday is that when you look at a parallel plate capacitance, so I have two plates here. The blue regions are the two metal plates, and in between is a dielectric. So this is length and width. So when you look at a parallel plate capacitance, there are two components to it. One component comes about because of these field lines that you see here. And the other component comes about because of this fringe electric field. And the fringe electric field also contributes, if there's an electric field, you know that there'll be a charge here and there'll be a charge here. And as you change the voltage, the electric field changes and the charge changes, and therefore you have a capacitance. So this fringe part contributes a capacitance, and then the rest of it, of course, you're well familiar with. So the capacitance then has two parts here. Epsilon by D that you see here is the normal capacitance that you're familiar with, parallel plate capacitance. That would be epsilon by D, capacitance per unit area, multiplied by W into L. W into L is the area of the plate here. Okay, so that's one capacitance that we are familiar with. Then there's another capacitance that comes about because of this fringe electric field here. So, it fields at the edges. And we call this capacitance per unit length, because that's not area dependent. Okay, because that's only at the edge. So whatever it is, let's say if we characterize it, we call it P here, P referring to at the perimeter. Okay, this is the area component and this is the perimeter component here. And this will get multiplied by the perimeter because the fringe effects will be there all along the perimeter part. So note that the capacitance has two parts. One is an area of the plate here and the other one depends on the perimeter here. Now, as you shrink the capacitor, if you shrink it by a factor of 2, you can see that the area component will shrink by a factor of 4 and this component will shrink only by a factor of 2. So as you keep on shrinking, what happens is that the area part scales faster as compared to the perimeter part, and eventually what you find is for very small capacitors, the perimeter part may become comparable or even larger as compared to the area part here. Okay, so when you go to MOSFETs of very narrow dimensions, you have to worry about capacitances having both area as well as perimeter component here. So coming back then, if we go back here, what we find is that if I look at this, focus on this capacitance here, PN junction capacitance. So there is a capacitance that will come about because of the area of this junction here. There is another capacitance that will come about because of the perimeter here. There's a perimeter here. There's a perimeter here, perimeter part here, and there's a perimeter part here. So there are going to be field lines here all along this edge. There are going to be field lines all along this edge, and there are going to be field lines all along this edge here. So we have to take into account, besides the area part, the bulk part, we have to take into account capacitance which comes about because of this perimeter here. I will not include this part here because this part, remember, is the overlap between source and gate. Okay, this part is the overlap between source and gate. It is already included here. Okay, so we will not look at this edge here, but we'll look at this edge and this edge and this edge here. Similarly, we'll look at this edge here, here and here. This edge here is already included here in this part. So when I talk about those source to body capacitors here, source to body capacitors, then now look at this expression here. Has two parts. An area part, which depends on the area of the source, Ls into W, and it has a perimeter part. Perimeter part meaning coming about all this along the edges here. And as I said, only 3 edges are involved. So the perimeter is 2 Ls, 2 times the source length plus W. Okay, so that's the perimeter that we are talking about here. And so there are two components then. Both of them are, if you recall your PN junction capacitance, both go, it's like a PN junction capacitance. This is capacitance per unit area at zero bias. This is the source to body voltage that you apply. PB is nothing but the built-in voltage here, and MJ is what is called as the grading coefficient. So all these values will be given to you, CJ, MJ, PB, all these are known. And similarly, CJ, SW refers to side wall. Side wall meaning, referring to these walls, the edges here. So CJ side wall, built-in voltage associated with the side walls here, and the grading coefficient associated with side walls. So these are just parameters that are given. MJ, CJ, SW, and all that are given. And therefore, if you know the source to body voltage, you can calculate the capacitance, provided you know the area and you know the perimeter. Okay, so you have to know and if you look at area and perimeter, they require W and they require also LS. They require that you have knowledge of how much is the length of the source. So if you have these two quantities with you, then you can determine perimeter, determine area, and determine the overall capacitance. Okay. Now, typically what happens is when you do design of MOS-based circuit design, so all the equations you will find they have W and L in them. If you look at the current is Kp W by L something, VGS minus VT square and all that. So when you do design of a MOSFET, after the design is complete, what you end up getting is a L value and you end up getting a W value. You normally don't get it. Nowhere will you see in the expressions for current that LS enters into the expression for current. Okay, where LS enters is in the capacitance here. So when you do a design, as I said, when you draw a schematic and you do a design, you'll get W and L, you don't get LS. The value of LS only comes that after your design is complete, then what you do is you go and do a layout like this here. You have to do a layout of your whole circuit, and after you do the layout, then you know, well, what is my area, what is the length of the source and what is the length of the drain. So after layout, these values become available to you, LS and LD, and then only you can compute the perimeter and the area, and then you can determine the capacitances here. So after a schematic design, you have to do a layout design, where you have to, you specify how these things are done. And but since in this particular course we are not going to do the layout, so the first order approximation, what we are going to assume is that LS is typically equal to L. This is not true in practice. As I said, you have to do the layout, but as a first order approximation, you can assume LS is equal to L. And therefore, once you do a schematic design, you have W and L, and you assume L equal to LS, and therefore you have perimeter and you have area, and you can determine the capacitances. The drain to body capacitance is something similar, exactly the same. Whatever happens at the source end, same thing happens at the drain end here. So we have the same expression. We have a term depending on the perimeter, a term depending on the area here. So we have two terms, and this capacitance then we can also determine. The other capacitance that you see here between gate and body, this is a small capacitance in saturation region and will not bother. Okay, its value is much smaller than the other capacitances, and as a first order approximation will neglect the capacitance which is there directly between the gate and the body. Okay, and as I said, there are different expressions in different regions of operation. I've given you we just talked about expressions in saturation region. Now these are expressions for linear region here, CGS, CSB, and all that in linear region. This is in the subthreshold or cutoff region here. All the values of the capacitances, it tells you how to calculate the capacitances in the subthreshold region here. But we will not bias a transistor either in cutoff or in linear or triode region. Our transistors would be biased in saturation, so we'll use these expressions here. Note that the expressions look complicated, but all that is there is nothing but a PN junction capacitance. If you know a PN junction, it's basically that expression here. Yes. Why did we? Yes, the capacitance, when you have emitter-based junction, you will have capacitance along the side as well. You're right. It will be there, there also. It's true. Okay, let me give you some typical values. So this is, you can see all the capacitances that are there in saturation region. CGS, CGD, C source to body, and C drain to body. Remove the sidewall term, should not be there. C drain to body and C source to body. So these are the capacitances that are there. And you can see, to calculate these capacitances, you need to know these values here. CGS0, CGD0. These are the 10 parameters that have to be known in order to calculate all the capacitances that are there. And these are the capacitance parameters that are provided to you by the manufacturer. The manufacturer will give you all the values that you see here, and so these are all available. As I said, then all you need to do is you need to know what is the length of this source, what is your length of the device L, what is the width of the device, and these expressions, and then you can calculate all the capacitances that are there. Let me give you some typical values here. You can see here this MOSFET, the length of the MOSFET is 1 micron, and the width of the transistor is 2 micron. Width here is 2 micron. In this case, I've taken the source length as 1.8 and drain length as 1.8 micron. And based on that, and the transistor is biased at source to body voltage is 0, okay, which means that source and body are shorted together. Drain to source voltage is 2 volt, source is ground, drain is at 2 volt. And based on that, the capacitances values, the transistor is biased in saturation region, the capacitance values you can see here. CGS is 4.1 femtofarad. The values are, note, the values are in femtofarad. These are small capacitances. CGS is 4.1 femtofarad. CGD is small, 0.43 femtofarad. Source to body capacitance is large, 4.47 femtofarad, and drain to body capacitance is comparable, 2.75 femtofarads. Now, CGD, you can see here, is small, between gate and drain is small, but if you recall that any capacitance which is, normally when you make an amplifier, you'll connect input at the gate and you'll take output at the drain. So CGD, remember, is connected between input and output and will get multiplied by the gain of the amplifier because of Miller's effect. So if you're building an amplifier with a gain of 20 or 30 or whatever, then that will get multiplied by that factor here. And even though it's small, it becomes important. Okay, CGD, even though it's small, it becomes important. All right. So CGS obviously is very important between gate and source. CGD is important. Normally what happens is between body and source, normally I'm saying the capacitance, body and source may be shorted. Especially for a PMOS. In a PMOS, body and source can always be shorted together, and therefore source to body capacitance doesn't enter into picture. In NMOS, sometimes you'll find source to body is there, sometimes it may not be there, depending on the potentials that are there. Drain to body capacitance is an extremely important capacitance, because note that most of the time the output is taken at the drain, and right at the output you have a capacitance which is connected, which is 2.75 femtofarad. So it's a very important capacitance here. And so these are the typical values here. So this is the complete large signal model. Remember, our large signal model was a current source between drain and source, a diode between source and body, and a diode between drain and body. And now what we have done is we've added all the capacitances. So between gate and source, CGS, CGD here, CDB here, and CSB here. So we've added all the capacitances, and for the sake of completeness, we've added a capacitance between gate and body also. So this becomes a large signal model that you can use for not just for DC and low frequency, but you can use it for high frequency as well. And if I take my small signal model and I add the capacitances that you just see here, it becomes a high frequency small signal model. Okay, so you add CGS, CGD, CDB, CSB. And as I said, this is a small capacitance in saturation, we will not worry about it. So 2 current sources, a resistor here R0, and these 4 capacitance here. That's what a small signal model of a MOSFET is under high frequency region. If the frequencies are small, you can of course ignore CGD, all these capacitances here, and you're left with these 3 elements here. Okay. All right. Okay. So now this model, it may seem to you that it's already too complex, but it's actually the simplest model that you can build of a MOSFET. MOSFETs have, the model that I've just described to you is what we would call as a level 1 model. I've told you that, for simulating circuits, we have simulation programs. And one of the popular circuit simulation program is what is called SPICE. This was, it was developed at University of California, Berkeley, one of the early circuit simulators. And MicroCap and many of the simulators that are there that came afterwards, they've either directly built upon SPICE or they're inspired by the SPICE, this particular simulation program. So there are a variety of MOS models that are built into SPICE or into MicroCap as well. If you go and click on a MicroCap MOS model, you will find that you can have a model which is level 1, which is the simplest model, level 2, level 3, then BSIM 1 and BSIM 2 and BSIM 3 and BSIM 4 and so on and so forth. Now what happened was when MOSFET started out in 1960s, the MOSFET channel length was large and level 1 model was reasonably okay. Now as MOSFETs have evolved, the channel lengths have shrunk, the MOSFETs have become more complicated, and people found that level 1 was not adequate. It was not adequately capturing all the characteristics of the MOSFET, so they had to come up with level 2 model. And that's how, as the MOSFETs have progressed, the models have also evolved in complexity. Okay. So, for example, for a 1 micron MOSFET, 1 micron, I was giving you these 1 micron channel length MOSFET, I was giving you these capacitances and all that. And some of the parameters that we will take are typical of a 1 micron MOSFET. Now, 1 micron MOSFET, a model which is accurate would be accurate is a BSIM 3 model. Okay. BSIM 3 would be accurate, while the model that I've provided you is level 1. Now, you may be wondering why not talk about BSIM 3. Okay. Now, the reason we are not talking about BSIM 3 is that the equations are complex. And if you recall, how would you measure the complexity of a model? Let's say this is a capacitance model. How would you say, if I give you 2 models, how would you measure the complexity? Which model is more complex? One way would be, how many parameters does it have? Right? If I had a model which had only 1 parameter, maybe you say, well, I have to plug in only 1 parameter and, the equation must be relatively simple. So one way of measuring the complexity of a model is number of parameters. Okay, so let me show you a BSIM 3 model. And how many parameters are there in BSIM 3 model for 1 micron MOSFET here. These are the equations. All right. These are elaborate equations that you see here. I've not given all the equations. I'm just giving you a sampling. But I'm sure you're going to like the next slide, which is the number of parameters. 99. These are the number of parameters in a 99? No, not factorial. That's an exclamation mark. Okay. So you can see all the parameters that are there. So the model is complex. And so this is for N channel and similarly for P channel. So the MOSFET's operation is complex. There are a variety of factors, phenomena that are there. And in order to capture all those phenomena, you need all these different parameters that you see here. Okay. So now the trouble is the following. If I take a 1 micron channel, 1 micron technology, the model is the accurate model is here and the parameters are here. But we know that this is too complex. We cannot remember our early discussion regarding models. This is an accurate model, but it's too complex. We can't use it either to design, either to analyze or design or understand the circuit. We can't do that. And the simple model that we just talked about, that is simple, that's easy to understand and use, but it will be inaccurate. So if you recall, we had a slide like this here, right? We had this slide, the role of the two models. So we'll use the simple model that I just talked about to do the design, initial design, and then you use the accurate model or BSIM3 model that I just gave you. You use that particular model to simulate your circuit. And then you check whether your design is correct or not by simulating it with an accurate model, and you iterate between changes here and simulation here. And once you verify that your design works with BSIM3 model, then you can go ahead and send it for fabrication. Okay, so we can't use BSIM3 model for initial design or for initial analysis. So we are stuck with level 1 model, and so you have to keep in mind that the design that you do with level 1 model, and once you simulate with BSIM3 model, there will be a lot of discrepancies. There'll be a lot of discrepancies, but using the simple model, what would happen is we would understand the circuit. We know now, let's say if the gain, if we simulate, you want a gain of, let's say 500 and you're getting 200, but through simple model, we understand the schematic. We know that if you increase RD or you increase the GM or decrease the current and all that, how to increase the gain. So using that, you can fine tune your circuit. Okay, so that's the model that we just talked about is a level 1 model, simplest possible model, and keep in mind that the predictions from that particular model quantitatively will not agree with what BSIM3 will predict here. Okay. All right. One more thing before we finish with our MOSFET. So models are over, but I want to point out a particular parameter called unity gain frequency. So this is I think we had discussed this in BGT also, unity gain frequency. The idea is as follows again. So you have a MOSFET, and you'll see the importance of this one. You have a MOSFET, and the MOSFET is VSS, let's say 0. So this is 0, this is VDD is 3, 4, 5 or whatever voltage. The transistor is biased in saturation region. So you apply a gate to source voltage DC, and there's a DC voltage here, and the entire transistor is biased in saturation region. Now, once you bias it in saturation region, you apply a sinusoidal voltage. Now what will happen is, because it's already biased, there is a certain amount of DC current flows. When you apply a sinusoidal voltage, the gate voltage will now have a sinusoidal component, and as a result of which, the drain current will also have a sinusoidal component. But in addition to that, the gate current will also have a sinusoidal component. Note that gate current doesn't have a DC component. DC component is 0. But the moment you apply an AC, the gate voltage has a sinusoidal component. And the reason being that between gate and source, I have a capacitance, CGS, and between gate and drain, I have a capacitance, CGD. And when you apply a sinusoidal voltage, you know that the capacitance is charge and discharge, so you start getting a sinusoidal current. So under AC condition, the gate current is not 0. You have a gate current here. And there'll be a AC drain current here also. So we define you can define a current gain, a AC current gain, which is the AC drain current divided by AC gate current. And note that all other voltages, AC voltages are 0. There's no AC voltage between drain and source. There's no AC voltage between source and body. Body is supposed to be shorted to source here. And the frequency at which this gain becomes equal to 1 is what we call as the unity gain frequency. Now, if you think about it, MOSFET is a device where you don't expect any gate current, right? I mean, it's an insulator. You don't expect any gate current. Now we are talking about a frequency at which the gate current is as large as the drain current. So obviously now the MOSFET is operating very, very far from its normal operating range. Normal operation is you have a lot of drain current, you have no gate current here. So people take this frequency as a upper limit of the highest frequency up to which a MOSFET is useful as a device. Beyond this particular frequency, the MOSFET cannot perform any useful function. It cannot have gain, it cannot give you power amplification, none of those things that you would want from a MOSFET will be able to do beyond a frequency of unity gain frequency. In fact, for most applications, you'll find the application will start to fail at a frequency which is maybe 4 or 5 times smaller than unity gain frequency. So in that sense, unity gain frequency is taken as the upper limit of operation, as a as a measure of the speed of a MOSFET. Beyond unity gain frequency, the MOSFET doesn't work. It's not useful anymore. So we would like to know then is what is this unity gain frequency and what does it depend on? Okay. So now remember, this is a small signal circuit here. We are talking about small signal drain current divided by small signal gate current. So what we can do is we can take our small signal model. We can take a small signal model. Just keep in mind, drain will be small signal ground, source will be small signal ground, body is connected to source, it will also be small signal ground. So that's what we are doing here. Drain is ground, source is ground, body is ground here, and gate is where we are applying the small signal voltage here. So we have this situation, and now we can simplify. Note that if drain is ground and body is also ground, this capacitor then gets shorted out, this capacitor gets shorted out, and so we can remove these two capacitors here. Not only that, R0 gets shorted, one end is ground, the other end is also ground, R0 gets shorted, and if you look at body to source voltage, that's 0. Source is 0, body is also 0. So this current source is open circuit. So, using all this, we can simplify to the following. So we are left with the following elements here. Between gate and body we have, between gate and source, gate to drain, and only current source is GM VGS, and that's it. Further, we can remove the CGB also, because gate to body capacitance is very small in saturation. We can neglect this also. So now, it's relatively simple. One can write down what is the gate current. Gate current is only capacitive, so it flows through CGS and CGD, and CGB also if you would like to keep it. So that's the gate current. And drain current that you see here has actually two components. One component is GM VGS, the other component is the one that goes through CGD. And one can build a more accurate expression, but the current that goes through CGD is small. So we've neglected that, and we've approximated it as GM VGS. So that's the drain current. And you take the ratio of the two. So you get GM, J omega, CGS plus CGD plus CGB here. And then unity gain frequency is the frequency at which this ratio goes to 1. So we make it equal to 1. And then we get the unity gain frequency F omega t, and Ft is here. GM by CGS plus CGD plus CGB. And as I said, gate to body capacitance is very small. You can neglect it. And I showed you also that gate to drain in saturation is 1 order of magnitude smaller than gate to source. If you recall, this was around 4 femtofarad, and this was about 0.4. So first order approximation, you can neglect even CGD and CGB as compared to CGS. So you're left with GM by 2 pi CGS, and you plug in all the the expression for GM and CGS, and you get this one, the final expression for unity gain frequency here. And this expression is important because it tells you what are the factors which affect the speed of the MOSFET. Because unity gain frequency is a measure of what is the highest frequency up to which you can operate your MOS transistor. And you can see now Ft depends on mobility of electrons in silicon. So if you want to build a very fast MOSFET, you should choose a material which has higher mobility. And if you go and read literature, people are trying to build MOSFETs on 3,5 semiconductors, gallium arsenide, indium phosphide, indium gallium arsenide, because those materials, they offer you a much higher electron mobility. So, but there are problems. The reason why you don't see those kind of MOSFETs is they have their own problems, and silicon MOSFETs are still dominant. So mu and mobility is an important part, but much more important part is what you see is L. You make a MOSFET faster by reducing its channel length. And that sort of explains, if you look at the evolution of entire your electronics, if you see, a constant trend has been almost like every year and a half or every 2 years, you will find that the channel length of the MOSFET is shrunk by a certain factor. And there's been a constant effort over the last 30, 40 years to shrink the channel length for 2 reasons. One is, as you shrink the channel length, your MOSFET becomes faster. As the MOSFET becomes faster, all your digital circuits, analog circuits, everything becomes faster. And the other reason is, as you shrink the channel length L, you can shrink the W also. So overall MOSFET becomes smaller. And when MOSFET becomes smaller, you know that you can pack more number of transistors in a given area. So you can make more and more complex circuits here. So channel length scaling has been one of the dominant features of electronics in the last, starting from 1960s. There's been a steady effort. As I said, it started from 10 micron or 20 micron, and now we have reached 22 nanometer. So started from there, 20 micron transistors, and we've reached 22 nanometer channel length. So steady decrease in channel length, and the resulting result has been faster and faster MOSFETs. Okay. Now, faster and faster MOSFETs here, and the other thing is mobility. All right. Okay. So for the MOSFET that we are talking about, if I calculate the unity gain frequency, turns out to be 2.8 gigahertz. Yeah, unity gain frequency. But as I said, you are seeing a unity gain frequency of 2.8 gigahertz. So do not expect your amplifiers to work at 2.8 gigahertz. When we actually go and build amplifiers, you'll find their frequencies will be in megahertz. Because note that this is only GM, CGS plus CGD here. When you build amplifiers, what will happen is CGD will get multiplied by the gain, and there are many, many other things that happen here. So actual operating speed of a circuit will be usually well below the unity gain frequency. So that's sort of a upper limit. You can't go beyond that. So, but you will not find circuits working at that particular frequency. Okay. All right. So that's the end of our discussion related to MOSFETs. And